Welcome to part 3 on vector applications. In this video we're going to look at an application of force. A force is also represented by a vector measured in pounds. If several forces are acting on an object, the result force experienced by the object is the vector sum of these forces. Let's read the example given. Tim and Rose exercise at CrossFit. One of their trainings is to pick up a 500-pound weight together for a few seconds. Tim is shorter than Rose, so they feel different amounts of tension on their arms. Let's use the figure below to find each tension. We see that T sub 1 has a lower angle, a smaller angle than T sub 2. So we'll go ahead and assume that T sub 1 is T sub Tim, and T sub 2 is the vector representing Rose holding on to the weight. The 500 pounds is pulling directly downward. So we'll call this a force representing the 500 pounds. Now I'm going to draw something called a free body diagram where Tim has an angle of 40 degrees for his tension, but if you measure it off standard position, it's actually 140 degrees. The tension for Rose is 62 degrees. And we have 500 pounds downward. We know that the tension in Tim's hands or arms plus the tension in Rose's arms plus the force of the weight downward is equal to 0, because when they pick up the weight, everything's balanced out. The weight is pulling downwards, the arms are pulling upwards and to the sides, and so everything is 0. Nobody's moving the weight at all, it's just stationary. Now we need to write the component form for each one of these tensions or vectors. The vector for Tim has an x direction component and a y direction component. If we think about it as how far the tension goes to the left, that's like your x component, and how far the tension goes upwards, that's like your y component. And so we can write the component form for the vector for the tension in Tim's arms just like we did before. The magnitude of T sub Tim, I'm just going to abbreviate it to a T, times cosine of 140 degrees. The tension magnitude for Tim times sine of 140 degrees. Let's find the component vector for Rose. We'll take the magnitude of the vector for Rose times cosine of 62 degrees, the magnitude of the tension for Rose times the sine of 62 degrees. Now remember, the magnitude of the vector scales the distance we're going in the x direction, the distance we're going in the y direction. Lastly, we have the force of the weight as a vector, which is 0 in the x direction and downwards 500. So we give it a negative 500. It may not seem like it, but remember, if we want to find the tensions, we would add up the components in the x direction and the y direction, but we have two unknowns instead of just one, and so we're going to create a system of equations. When we sum up the direction or the components for direction of x, we will get an equation because we know that the sum of the force in the x direction equals 0. We also know that the sum of the force in the y direction equals 0. And so we can set up a system of equations with this information. First, let's start with the system for x. This gives me the magnitude of the tension for Tim times cosine of 140 degrees plus the tension magnitude for Rose times the cosine of 62 degrees. We know that if we were to add that to the force downward, which is 0, we get 0 in the x direction. That represents the sum of everything I highlighted in yellow. Now we're going to add up everything I highlighted in blue. The system for the y direction will be the tension magnitude for Tim times the sine of 140 degrees plus the tension magnitude for Rose times the sine of 62 degrees plus negative 500 equals 0. Now, you may be wondering what in the world I'm going to do with this. I'm going to turn this into a system of equations in a matrix. Now, some of you may have not used matrices before, but it allows you to row reduce or simplify a system of equations extremely fast. Because we know that the tension for Tim's arms is represented in the first column, and the tension in Rose's arms is represented in the second column of the system of equations, then we can just write this as cosine of 140 degrees, cosine of 62 degrees, and we know that this is equal to 0. We can think of this last column as the equals column, and so now we are going to pull this 500 to the other side since it doesn't have a tension connected to it. So this will be 500 on the right of the equal sign. We're also going to put sine of 140 degrees, sine of 62 degrees equals to 500 because I brought 500 to the other side of the equal sign. And then I'm going to do something called row reduced echelon form. And I'm going to do that in the calculator. It just solves the system of equations, and I'll show you an example in the next video of how to do that consistently for any setup. The first thing you want to do is make sure that your mode is in degrees. And then you want to go to second matrix, arrow to edit, and then define the dimension of your matrix. This has 2 rows and 1, 2, 3 columns. So I'll need a 2 by 3 matrix. Then I'll enter the values given. Cosine of 140, cosine of 62, 0, sine of 140, sine of 62, 500. Then we'll do second quit, second matrix, math, and then we'll arrow to row reduced echelon form, which is this one right here. And then we'll select the matrix and hit enter. If we round to full values, these will be 240 and 392. You may be wondering now, why doesn't this add up to 500? Well, they're also pulling against each other, and so they're not just fighting the tension or the force downward of 500, they're also fighting against their own pulling, opposing each other. So that's how you solve something like this. It's kind of cool that you can find the tension. You could do this for tension in a rope if there's something hanging in the middle as well. It's kind of a cool way to solve them.